Okay, so let's review. We begin with a group G. Group G has elements, for example, alpha and beta, and because it's a group, I can take any two elements and using the group operation, I can produce a third element, gamma. And I've been calling the function that does that phi, which takes two group elements, alpha and beta, and it produces a gamma. So I've been drawing it this way. And in the green, I'm intending to mean the abstract group. This is what I might say is rotations in space. If I take a rotation alpha and a rotation beta, if I execute alpha and then beta, I get another rotation gamma. And I call this abstract group G. And then I think hard and I realize, you know what? Every element of this group can be parameterized and the group itself is actually a manifold of dimensionality equal to the number of parameters. And then I introduce charts on the manifold or charts on the set, and I map those charts into R eta, and that's what a manifold is. So usually the fancy language is introduction of charts. Sometimes if you study this using separate books, you'll see them say, once we choose charts or introduce charts, what you're basically saying is you're creating a coordinate system on G. That's a fancy way of saying it, because they like to break it up into the topology of it where, there's multiple charts. You can't do it all in one chart, so you need a couple. So you choose charts, and each chart has its own psi. And psi are the chart mappings, right? So this is what we mean by the manifold G. And then we kind of stop thinking about this, and we start thinking just about everything in Rn, actually. So every point alpha we think of as its coordinates, alpha 1, alpha 2, beta, beta 1, beta 2, gamma, gamma 1, gamma 2. Obviously, this is an example of a manifold where eta equals 2, right? But we don't restrict ourselves to that. I'm thinking in the general abstract. Now, also, G, just being a manifold is not quite good enough to be a Lie group. It does have to be a group, and it does have to have a manifold. But this function here has to be continuous. And what's interesting about that is, and it's worth kind of talking about, is when we think about continuity, because it's a manifold, we're really kind of thinking about continuity on Rn. So what I mean by that is, well, R eta. I said Rn, but I mean R eta. You can think of the group, this mapping, as a mapping from 2 points of the group to another point in the group. However, when you think of it in terms of topology and continuity, continuity was always a set and a function into another set, and there's a function that goes from the first set to the second set, and we know the function is continuous if open sets in the range. If the inverse of the function brings it to open sets in the domain, that's when a function is continuous, assuming it's also one-to-one and on-to. So for it to be continuous, you need to be, well, it doesn't have to be one-to-one and on-to, I'm sorry. It just has to be open. Yes, continuity is, that what I just described was a homeomorphism, right? One-to-one on-to with a continuous inverse is a homeomorphism. That's not what we're talking about here. We're just talking about a continuous function. So I would redraw this just to fit that picture. I would redraw the group G as like a second set, and then this becomes a mapping from one set to another. So we would make it kind of look like this, and then there's another mapping, by the way. It would go from, say, beta to beta inverse, right? That's got to be, we should call that the inverse mapping. Say I wrote that as inverse beta, right? So there's a mapping like that. Those two maps have to be continuous. And just to walk the dog through this, look, I don't mind repeating myself and just making more lectures and having them go on a little bit longer. That's just my style. It's not efficient in some sort of information density way. So just bear with me. But I don't mind going back and reviewing it and making slow, steady progress. Hell, I've been doing this all my life, right? I don't hesitate to waste time on it. But let's look at this inverse map. This inverse map has to be continuous, right? So what does that actually mean? Well, continuity means if I have an open set over here, then the inverse of the inverse map should give me an open set over here, right? That's what continuity is. So I'm looking for the ironically named thing, inverse of beta right, has to be an open mapping, meaning open sets in the range have to end up over here. Open sets in the range of the inverse function have to be open sets in the domain, right? So with these things, these are the abstract sets now. And I use sets as a plural, right? But this is the same set as this set. I'm just trying to lay it out this way so we can think of it in terms of the topology that we've learned in the past, right? Topology almost always has two sets, one on the right and one on the left. If it's the same set, that's fine. You could kind of loop these around so that they're all going to the same set, but it's easier to lay it out this way. But what I'm actually talking about is over here somewhere is the coordinates of beta inverse, right? And those coordinates maybe I call beta inverse 1 and beta inverse 2, right? That's the coordinates of the point beta inverse, right? And it lives in, it's got coordinates, right? So when I talk about the inverse mapping as continuous, when I talk about it for a manifold, I can actually use the open sets on Rn, right? The open sets around beta here. Let me, it's not easy to see. Let me use blue, right? The open sets around beta here, I inverse map it, and I better get an open set around beta over there. The open set around beta inverse here, better inverse map to the open sets of beta over here. And so when I think about the topology of continuity, when I talk about the continuity of these functions, this inverse function and the group operation function, I'm really thinking about continuity in terms of Euclidean space, because that's what a manifold gives you, right? The manifold gives you that power to think of open balls around points in R eta. And these guys correspond to actual group elements through the chart mapping psi, which are homeomorphisms, which means they're not only continuous, but they're one-to-one and on-to, right? So they're really, really important. But they're so important, ironically, that they kind of fade into the background. But the reason that they can fade in the background is because what they've done is they've taken our mind away from here and just put us right here, where all we think about now is everything in terms of coordinates. And so the inverse function B is really now inverse beta 1, beta 2, right? That's the function we're allowed to think about down here. And if we really want to get up into here, we have to think about inverse beta 1, beta 2. Let's see, say we started here, right? Say we start in this with these coordinates. Inverse beta 1, beta 2 first, and then you would say psi. So it would be psi after inverse beta 1, beta 2, and that would take us from here up into here in principle, right? And then you could go from here up into there by saying you would start with psi, right? So it'd be psi and then inverse beta and then psi inverse. Oops, yeah, I'm sorry. This has to be psi inverse after inverse, where inverse is the name of the function that takes a group element, coordinates of a group element, gives you the coordinates of its inverse, psi. So the point is, we don't talk about any of this anymore, right? This is so embedded in our thinking, this nature of manifolds, that we don't, this whole mess that I just went through, you never see that. You just talk immediately about these things usually. And sometimes it's just implied. Now, it is important actually to go way back into this abstract stuff. And Gilmore does not do it. There is a whole development of Lie theory that just lives in the abstract. And it does actually talk a lot about the manifold structure. And I'm going to do that. I've decided that for anybody to go through and study Lie groups and Lie algebras, my goal is to make it so it's a little more, a little bit more than like the rough stuff you get in a physics class, right? And you should be able to go out there and read different books and papers. Well, read different sources for all this stuff. And I want you to be comfortable with all of those things. And there's no way to do that without doing at least a few lectures on just the abstract theory. The problem is the abstract theory is so ad hoc looking that it's probably not a good place to start. It would be a good place for a mathematician to start because they would develop it so fundamentally that it wouldn't be ad hoc. It would just be super, super abstract. The approach we're going to take is we've gone through this kind of stuff we've gone through a very practical introduction, and then we'll do the abstract part for a few lectures. Okay, anyway, so where were we? All right, so we're talking about the nature of this. We started with the nature of this Lie group, and now we've reviewed it a little bit. We've redefined what a Lie group is. It's a topological group that is also an eta-dimensional manifold, and we've described in detail what that means. But the critical thing is that the function that takes any group element to its inverse is continuous, and the function that takes any the group operation function is also continuous. And we now understand, look, continuity, we're thinking about it down here, and we're allowed to because it's a manifold. And, well, really, just to put another point on it, is psi is a homeomorphism. And that's what the strength of a manifold is. The point is you can't always make a psi. That, just to remind you about manifolds, just because this is a continuous, well, I can't call it a continuous group. What I say, just because this is a group with an infinite number of elements that can be parameterized, doesn't necessarily mean it's a manifold, right? You know, the fact that you can map this thing homeomorphically onto R eta is an important feature of all this. Not every infinite group can get a psi. This isn't a trivial step. This is, you know, in principle, you should have to demonstrate this. You should have to demonstrate this one way or another. But we're beginning with the presumption that we have continuous Lie groups, so that means we assume they are homeomorphic to R eta. Okay, all right, so we started by introducing these topological groups. That's what we're calling them, topological groups. And the topology is all the topology inherited from R eta. And it's got a dimensionality of eta, which is the number of parameters needed to identify which member of the group you're dealing with. So then we took the next step. We said, you know what? Let's just think of this as a group of matrices. Now, there's actually two ways that we can think about this as a group of matrices. We can think about another mapping that takes us from the original group into a group of matrices. And you can think of again, as usual, this totally abstract group. And then you can think, okay, each group element now becomes a matrix. So the group element alpha gets mapped through this to a matrix that represents the group alpha. And the idea there is that ultimately this group acts on a vector space, and vector spaces can always be interpreted as column vectors, and therefore if it's going to act linearly on a vector space, then you can interpret it as a matrix. So it's very common that you'll see in the literature the abstract group element, the matrix representation of that abstract group element is given with an M. And then you have to choose, okay, what's the dimensionality of these matrices, right? You have to choose a dimensionality of the matrice that you're going to use to represent the group. And you usually have a lot of choices. And in fact, probably most. I got to be careful when I say most because I don't know of every Lie group in the world. I haven't completely categorized all Lie groups. The categorizing Lie groups is actually one of our important topics coming up. But most of the groups I'm familiar with can take an infinite number of different choices of n. Any finite number n can be used to create a matrix that represents a Lie group. In fact, in the example we did that Gilmore does earlier, right, the example that went e to the alpha 1, alpha 2, 1, right? We learned that was just a two-dimensional representation. And then I think I showed you how to make an arbitrary integer representation of the group. It gets a little unwieldy, and it's not clear why you might do that, why you wouldn't just stick with the small one. But that question aside, the point is that your choice of the dimensionality of the representation for our purposes right now is somewhat arbitrary. You can choose it to be arbitrary. But the problem is, the reason I'm harping on this is the problem is n is a dimension. It's a dimension of the matrices that represent these elements, but it's not eta, right? We went through that. Eta is the number of parameters needed to calculate every matrix element for this group, right? For this matrix, right? So, you would have alpha 1, 1 all the way to alpha n, n, and each alpha I, j is a function of these different parameters, right? And those different parameters would be alpha, I guess the way we're doing it, alpha 1, alpha 2, dot, 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 all the way to alpha eta, right? Where these are the coordinates of the point alpha, mapped through psi of alpha, right? This thing here is going to be an ordered pair, alpha 1, or an ordered eta tuple all the way to alpha eta, right? That's what this mapping psi gives us the coordinates of that point. And then each matrix element, alpha ij, where now alpha ij subscripted represents a matrix element, and the parameters that calculate that matrix element, well, there are eta of them, right? But the size of this matrix is sometimes called the dimension, but you can't confuse that with this, right? I harp on that because, hey, I did it. I made that confusion, and I presume that if I made that confusion when I was learning this, so did everybody else, because I'm just praying to God everybody's as dumb as I am. Okay, so let me. So this is one way of looking at how to create the matrix group. But again, this mapping from this abstract thing to the matrix thing, it's we don't really think about it that much, and so we can actually take this whole thing and simplify it. All right, so what are we going to do? Well, the first thing we're going to do is we kind of erase this, right? We erase that, and then we take the matrix group and we kind of go boop, like that, right? And once we've done that, we kind of erase this M sometimes, and we're basically calling that G. So G is now a group of matrices, and we've kind of removed this abstract element, and now it's just an assumption that, well, it's not an assumption, it's just, that's our picture now. We now are saying, when we look at it this way, we're saying the group of n by n matrices with a certain property is a manifold. And we're now mapping the matrices through psi directly onto Rn. And so there you have it. That's probably the way we want to look at this for this course. We want to just go right into the matrix, kind of skip all that architecture. And in fact, once you kind of live in here, right, and then even this, God darn it, even this stuff goes away, right? And we just say, oh, this is a group of n by n matrices that have coordinates on it, right? The alpha 1 coordinate, the alpha 2 coordinate. Actually, I'm using alpha to represent the coordinates of a point alpha inside, or of a specific matrix named alpha. So I kind of need a name for the parameters inside there. So maybe I would say coordinate mu1 and coordinate mu2, something like that, right? And now that is probably where your head needs to be right now, is you assume the group is a group of matrices that have a coordinates laid out, and that every point in that coordinate system, right? I'll mark it, say red, say that point or that point or that point. That point represents a full-blown matrix of n by n, where n is some choice that we've made, and each matrix element is calculated independently using the coordinates of the point. So, for example, that matrix element would be, say, we would call, say, this is the point in there, alpha. So the mu1 coordinate of alpha would be given by, say, x, and then the mu2 coordinate of alpha is given by y, then this point here would be alpha 2, 2 as a function of x and y. That's if eta was equal to 2, right? Okay, so that's where our head is. Actually, maybe I'll make this whole lecture just a review of all this stuff, okay? Okay, so here we are now back with, this is our new thing, right? This is my new little picture for how this is going to work, right? The group G, coordinate system on the group G, each point is a matrix. The group operation is now mimicked by matrix multiplication. So this thing that I was drawing in the past that looked like this with phi alpha beta, right, going to gamma, right, that thing, that's now going to be the matrix for alpha multiplied by the matrix for beta, gives you a matrix, and that's gamma. So this is matrix multiplication. That's the group operation. Interesting point that somebody actually asked in the comments of my last lecture. These are matrices, and you multiply them and you add them and subtract them exactly the way you normally would. However, there is no such thing as matrix addition here. This does not exist. In fact, I'm going red on that. This does not exist, right? The group operation is the only thing that exists in the group, and that's the function phi, and that's mimicked by multiplication. The operation for inverse, right? I think I was calling it inverse. I really wrote a big check for that. That's an annoying way of writing the function. But the inverse of alpha, which equals alpha inverse, right? That function is matrix inversion, right? That is going to equal now the inverse matrix, right? Using the normal methods of calculating the inverse matrix. So these functions are now, we're going to think of them as all internal to G, just like that. And there's only two operations. Matrix multiplication, which mimics the group operation, and matrix inversion, which mimics the inversion function. And because all of the matrix groups we deal with, right, remember, so going back to our first few lectures, we're always dealing with some subgroup of the general linear group acting on a vector space V, R, right, or C, or I guess we also included the quaternions, right? These guys are non-singular, right? They're non-singular. So the reason, now you see why that's so important. Otherwise, you can't invert. If you can't invert, you cannot have a group, because every group, every element has an inverse. So that's why this is so important when we think about matrix groups, right? Non-singularity is what's so key. All right, so next step. All right, so then we learned that once you have this matrix group, we had a simple process that we kind of spent some lectures on. Okay, so I need a variable for the parameters, right? So I'm gonna say that the parameters of this group are, I went with mu before, right? So mu I, so that would be like, say, mu1, and this parameter would be mu2. But mu I, the parameters are going to be called mu I. That means every point in there is given coordinates mu I of, say that's going to be the matrix alpha. Mu I of alpha is literally the coordinate, the I coordinate of alpha. All right, so anyway, I need that because I need to be able to take the derivative with respect to it. So now we know that if I take that matrix, and this derivative of a matrix means I'm taking the derivative of each matrix element one by one with respect to this one parameter mu I, and then I evaluate it at mu equals 0 after the derivative is taken, obviously, elementary calculus there. And then I end up with a matrix, right? This process will give me another matrix. And if I do that for each mu I, I will generate eta matrices, x1, x2, x3 to eta, because I can do it eta different ways because there are eta coordinates, because this is an eta dimensional manifold. In fact, I should mark that down as eta dimensions. Let me erase this here. So there's eta dimensions there, right? So I can create eta different matrices using this formula. I take those eta matrices and I wrap them up in a box, and I call that set. I call the set of all matrices that are spanned by these eta matrices. I call that whole set script G. It's really Gothic G is what I want, but no way am I going to do that. I'll call it script G. And all the guys spanned by that, all of the matrices spanned by these guys, linearly spanned by these guys, create a vector space called script G. And we talked a lot about that. And it's pretty easy, right? This was a really simple process. If you knew how these matrices elements all depended on these parameters, this derivative is totally trivial, and you'd quickly capture the generators of script G. But what we also showed is that, okay, so while we're over here, the arbitrary element in this, say an arbitrary element y of this vector space is always going to be, say, y, I, x, I, right? It's a vector space, right? So every element in the vector space can be broken down in the components. The one new thing we'll discuss today is heavily based on that, right? Heavily based on that. So now what we've discovered this space using this rule, and we motivated that rule in the previous lectures. But remember, this is how we went about discovering the Lie algebra. Well, this Lie vector space, right? And then we discovered that, wait a minute, you know what? Because of this definition, the reason this definition was motivated is I could take any element of G, which means not just the generators, but any linear combination of the generators. And I can say, you know what? If I write down, I'll do this in blue, the identity matrix plus epsilon times some element G, where y is an element of the Lie algebra. I'm going to call this a Lie algebra, even though I haven't reviewed the bracket yet, right? But this is the Lie algebra, right? We're going to remind ourselves why it's an algebra in a moment. This guy here is a matrix, right? Because y will be a matrix through this. It'll be the sum of a bunch of matrices that are the generators, each multiplied by some real number y, right? This will be a real Lie algebra. It could be complex number too. In fact, thinking about it in terms of complex numbers is fine. So the point is it's either real or complex, depending on the nature of a variety of things. But thinking about it in terms of reals is probably the way to go right now. This guy here, if epsilon is small, this guy here turns out is actually an element of G, right? This is an element of G that represents an infinitesimal group operation, meaning it's infinitesimally close to the identity. So when we do this addition, we're actually producing a group element over here. So in some sense, we have a map that goes this way, but it's a very restricted map, right? Because this map here, this map in blue, it doesn't produce every element of G. It only produces those elements of G that are right around the identity. I used to use the red for the identity. I'll use green now. That's the identity in G. We'll call it I. Sometimes they call it E, right? We'll call it I. That's the identity. So if I take a neighborhood around the identity, an infinitesimal neighborhood, anything in that neighborhood, anything in here, it's a matrix, right? This is a matrix group. This this is a matrix group. So anything inside this matrix group is a matrix. Anything inside this little spot, infinitesimally close to I, that matrix that's in this group is this, right? So this line doesn't take us from any, well, actually, no. This line will take us from any element of this Lie algebra, any element of this Lie algebra. You got to slap on this tiny number epsilon, right? So whatever this is, right, these y's could be gigantic, right? But this epsilon is so small that this matrix looks an awful lot like 1, 1, 1, 1, etc. for however many dimensions you have, right? This is n by n, where n is our choice, right? It looks very similar to this. And by very similar, what I mean is that these off-diagonal elements, these guys here, right? All of those guys are going to be epsilon times something. So epsilon is always going to be really, really small. So this whole thing is going to be really, really small. And when I say really, really small, what do we mean? Well, we mean we're kind of limiting epsilon towards 0. And it's got to be small compared to 1. And remember that these group elements are matrices that operate on a vector space out there, right? So those changes have to be small relative to some norm. I mean, there's all kinds of ways of talking about what small means. But the point is we've got this epsilon, which we can choose to be arbitrarily close to 0. So I guess that's the mathematician's way of saying it. Epsilon can be chosen arbitrarily close to 0. Ergo, by definition, this thing is small. Physicists would want to be like, oh, it's small compared to the size of Betelgeuse, or something like that. Meaning, but that's obviously not going to work for us here. Okay, so this is one way to get from the Lie algebra into the Lie group. But now we want to talk about how to get to an arbitrary element of the Lie group. And when I say talk about it, I say we want to remind ourselves because we've already talked about it. So the general map that goes to the entire into the entire Lie group, which I'll sort of draw as like a thicker blue, bunch of thick blues, right? That is the exponential map, and it's written different ways in different books, but it's exponential, and then something like this: the exponential of y, where y is an element of the Lie algebra. And we saw how that process worked. It's actually kind of a rough process. We're going to do, I think in our next lecture, we'll do 2 examples. I'm just probably going to work just to have enough time to work through my review in this lecture. So this exponential, that idea is to get from any member of the Lie algebra into the entirety of the group. And there's some important concepts here. There's some concepts that have to do with compactness and non-compactness and one-dimensional subspaces and things like that we'll slowly start attacking. But you just need to understand these different maps. Okay, what else? Okay, yeah, so now the Lie group, this Lie group here, this Lie algebra here, we've got to get to the word algebra, so let's remind ourselves about that. Oh, I guess I should point out, this is a very, very precisely defined object that's defined exactly this way. It is literally the power series of the exponentials, the exponentials Taylor series applied to this matrix, right? And this is a matrix. Don't worry about, when you sum this out, you get a single matrix, so you're raising matrix to matrix powers. And this is a number, so it's an integer, so you got a factorial in there. And then, of course, you sum from, I guess I should have written from n equals 0 to infinity in principle. So this is not a totally easy operation, but then again, it's elementary in many ways too. So, well, at least for the examples we're going to do, it's going to be tractable. Okay, so that sort of puts a point on this, and we will come back to this with 2 examples in one of the very soon to upcome lectures. But in the meantime, what we showed is that there is an operation called the bracket operation. And the bracket operation between 2 members, I guess, z and y, was defined as the matrix Z multiplied by the matrix Y minus the matrix Y multiplied by the matrix Z, where this is the regular matrix multiplication. This is matrix addition, and this, of course, is matrix multiplication. And this whole process here is the bracket of Z and Y, right? And what we discovered is that although this matrix product is not necessarily a member of the Lie algebra, and neither is this, the difference between these two matrix products will always be a member of the Lie algebra. Ergo, this bracket operation is closed within the algebra. And that's, of course, what you need to have a binary operation inside. If you have a vector space with a binary operation that is closed, you've got yourself an algebra, as long as that binary operation is linear over the matrix addition. In other words, so G is a vector space with a vector space addition and a scalar multiplication, which we can think of as over the real numbers right now. So we've got our bin of real number scalars, we've got scalar multiplication, we've got vector addition, and now we have what we would call vector multiplication, right? So we might say Z multiplied by Y is defined as ZY, right? So this becomes our multiplication operation, which turns this into an algebra, as long as Z multiplied by Y plus W equals Z multiplied by W. Like, oops. So this linearity has to be true. And it is, right? We showed last time, we went through a trick to show that not a trick, but it was tricky to show that Z and Y were inside this space. And actually what's interesting about the proof we did last time to prove that this was closed, right? To prove that this was closed, we invoked a series of steps, including a topological statement at the very end. If we study this whole thing in the abstract, purely abstractly, without going into the derivative of matrices and things like that, it's actually not quite as hard. I mean, it's hard in the sense that all the abstract stuff is hard, but given the sort of the foundation of the abstract stuff, the benefit is proofs like that aren't very difficult, and I'll demonstrate that eventually, not too long after we do our examples. All right, so we're almost ready to get to our new stuff today. The last thing I'll say before we move on to the new material is what's interesting is the way we've presented it. It really feels like the Lie algebra is just sort of a tool to understand the Lie group. And sure, no doubt. On the other hand, if you're a physicist, you will almost spend all of your time working with the mathematics of the Lie algebra. We haven't even scratched the surface of the Lie algebra. And I haven't even provided the abstract definition. I haven't mentioned, for example, this is not even associative. You know how groups have to be associative? Well, it's a group operation under addition, and it's certainly as a vector space associative under addition. But this guy here, this is not associative, which would mean associative would mean Z Y W, right, would have to equal Z Y W, right? In other words, doing the order of the commutators here matters a lot, right? So we haven't discussed that, but it's still an algebra. It's still an algebra. In order to be a true Lie algebra, it has to be non-associative in a very specific way. So we'll get to that. Well, we defined the Lie group really completely. We said, hey, it's a group. It's a manifold, which the word manifold immediately means it's continuous because it's a manifold. It's homeomorphic with R eta. R eta is a continuous space. And we said that, it's a group that's homeomorphic to R eta is really what I mean there. what's continuous is the group operations continuous, and the mapping from any element to its inverse is continuous. Right? We are very thorough about that. The Lie algebra we just derived in little fits and starts, right? We first came up with these generators of the Lie algebra, and that became really the basis of the Lie algebra. And we say basis because Lie algebra is a vector space, so this is the basis of the Lie algebra as a vector space under addition and scalar multiplication. Then we introduced the commutator, which becomes the bilinear product of two vectors, which is not a real number. It's a vector, right? Remember, we had inner products before that would take two vectors and give you a real number, right? Or whatever your bin of scalars is, could be complex. That's not what this is, right? This gives you an element of G, right? This is a bilinear operation, but it's not an inner product. We have yet to define an inner product. We can, because this is a vector space, so we can define an inner product, and believe me, we will. It's really critical how defining the bright inner product here. That's how we characterize Lie algebras. But as physicists, we almost live here and study just this and everything about particle physics, where you talk about representations of different Lie groups that are out there, continuous groups that are relevant to physics, that describe different particles and different representations and all that stuff. It's really done here. And we just pay homage to the fact that these guys generate certain symmetries. And that's not strictly speaking, right? I'm just saying, as you learn it, you really feel like you learn this. And when you study quantum mechanics, right, from the get-go, you really start here and you learn about angular momentum algebra, the algebra of angular momentum. That's all here. There's definitely quantum mechanics books that make the point about this group, so I'm not disparaging all quantum mechanics books. It's really, different ways of approaching the subject. But the point is the reason I'm bringing all this up is just we started here and we developed this, but I want you to start thinking of this and this sort of co-equal concepts. There is the question of the circularity of these mappings, right? In other words, you go from the group, you always get a Lie algebra. It's unique because this is a unique process. The problem is going back from the Lie algebra. If I generated every element of the Lie group from the Lie algebra, there's a bit of a problem because it turns out there are several different Lie groups that can give you the same Lie algebra, right? And so we have to kind of nail that down. So this isn't perfectly circular, right? It's not guaranteed. Sometimes you've got to understand that you can start with a group, get this Lie algebra, and then come back and you'll get a different group. But obviously that group is closely related to whatever group you started with, and we need to understand those relationships. So I guess what I'm getting at is there is a problem like this, right? You have a Lie group 1 and a Lie group 2 and a Lie group 3, right? And then you go through this red process, and they all get you to this Lie algebra, right? But this Lie algebra's inversion only brings you back to one of these, right? So the exponential takes you back to one of them, but there's multiple groups that take you in here. So now the question is well, how do you understand going from one of this one group to these others, right? And we need to talk about that a little bit later too. Okay, so now let's just break into the last thing I wanted to talk about in this lecture, which are the structure constants. This lecture's gone on too long. All right, we start with structure constants next time. I will title this lecture Review, so people who feel like they understand everything can skip it. And we'll just talk about the structure constants next time.